Ready?
Yeah, anytime.
Okay. All right, hi everyone. Thanks for joining us for the last seminar of the seminar series for the spring semester. So there will be things coming up during the summer, but if so, look for that from Colleen, and they'll be sending out announcements regarding that. So today we have David Shea from Kraken Sonar, and I'm going to read his bio and then let him take over. So David Shea is the Vice President of Engineering for Kraken Sonar, Incorporated, a leading developer of interferometric synthetic aperture sonar technology. David has extensive experience in the design and manufacturing of sonar systems and unmanned underwater vehicles, and has integrated and operated synthetic aperture sonar onto a variety of towed and untethered platforms. And previously, David was the engineering manager at Marine Robotics Incorporated. Right.
Thanks, Shannon. As Shannon said, I'm Dave Shea. I'm the VP of Engineering for Kraken, and today we're going to talk about high-speed, high-resolution seabed mapping using commercial interferometric synthetic aperture sonar, or as you'll see in the presentation, INSAS is what we generally refer to it as. So a little bit of background. Who's Kraken? We're a relatively small company. We're based in St. John's, Newfoundland, which is on the very east coast of Canada. We're about 30 people there now. We've got offices in Boston. Jeff Bartowski, our Director of Business Development, is here from that office, and we have offices in Germany as well. We're a developer and designer of synthetic aperture sonar products and systems and technologies built around that. You can see, I won't go through all of them here, but the focus today is going to be on our miniature interferometric sonar system, as well as our Katfish, our active towfish system. So we're a relatively young company. We've been around for about 4.5 years. We started in 2012 with about 8 employees, so we've been growing rapidly over the past few years. And as I say, our primary technology and everything that you're going to see today is based on our synthetic aperture sonar. So you can see most of the platforms that we're working on. SAS, the largest market for us is definitely military and defense, mostly for mine countermeasures, mine hunting work. These are the images that we're allowed to show that you'll see here today. So these are mostly commercial systems. This is actually owned by our Canadian Defense Research and Development Agency. That's a fairly large Arctic Explorer AUV, and I'll show you some of the data we actually collected in the Arctic with that system. There's an active towed platform here, Minas 600, that's actually from Rhode Island. Newark uses that system, and another Minas 600 from the Australian Navy there as well. So before we get into all the pictures and the details and some of the technical specs, I want to back up a little bit just to give you a briefing on what is interferometric SAS, for those of you that might not know. We view SAS as, in interferometric SAS, as really the convergence of a bunch of different technologies. It's got kind of the best of many worlds, and it's comparable to a multi-beam in that you get bathymetry out of it from the interferometry. It's comparable to a side scan in that you get very high resolution backscatter or imagery from the side looking systems. And it operates somewhat similar to a typical swath bathy or an interferometric bathy system. So the fundamental cornerstone of SAS is the synthetic aperture part. So what we do is we use a physical aperture or a physical array, and the array length can vary depending on the system that we're deploying. And we use the software to trick the system into thinking that array is much, much longer than it really is. By doing that, the way in which we do that, we use a very broad transmit beam, and we're pinging much faster than the vehicle is moving as it's moving through the water. So we end up with a lot of overlap, ping-to-ping overlap in the system. Because we have all of that overlap, we can recombine those pings in software, compensate for the motion of the vehicle, and make it look like it all comes out of a very long acoustic array. And I'll show you why we want to do that in a second here. So to understand why we build that synthetic aperture, you want to understand what is a side scan sonar and how does side scan work. Well, fundamentally, side scan is a side-looking sonar array. You can see an example here on a Minas 600. The resolution of the system is driven by both the beam width and the range. The beam width is inversely proportional to the length of the array. The longer the array is, the narrower the beam width. The narrower the beam width, the higher the resolution. There's also frequency plays a factor in that as well, which was why you see that the wavelength included in that equation as well. So this is all well and good. There are lots of side scans out there. With typical example, we use a 1 meter array. The problem with typical side-looking systems, you have a finite beam width, and that beam width spreads with range. So you can get very good resolution close to your platform. The further away you get from the platform, the worse the resolution gets. And there's a solution to that in that you can build a longer array, but a much longer array obviously costs more to build, it's more difficult to manufacture, and you have to put it on a fairly large platform. So just rough numbers here, at roughly a 300-meter range, a 1-meter array at the frequencies that we're using would get you about a 1.9-meter resolution. Double the length of the array, you'll have the resolution. Double it again, 4 meters, you'll have it down to the 0.5 meters. So what we do with synthetic aperture is we're able to build an array that's up to 25 times longer than what the actual physical array is. So we build an array that's up to about 50 meters long, and at 300-meter range, that gives us a resolution of 0.03 meters. And what we actually do is we build this array artificially in software, and then the further away we get from the platform, the more of that array we start taking and using to continuously narrow the beam width to maintain a constant resolution across the entire swath. So you'll see some of the images, and this is an important property to keep in mind, because one of the big differences between SAS imagery and typical side scanner multibeam is SAS has a constant resolution across the entire range. So whether you're 10 meters away or 100 meters away from the platform, the resolution is constant throughout the whole swath. So SAS is really an evolution of side scan sonar from back in the 70s when they originally developed analog side scan systems. Moving in from analog to digital systems gives you a higher signal to noise, a lot of benefits there, and then moving from digital side scan systems up to multi-ping systems, which some of you are probably familiar with, and into military synthetic aperture sonar. What we took some of these, so when we talk about SAS, we didn't invent SAS. Lots of other people have been building SAS for a number of years. The problem is that it's been typically reserved for military purposes, meaning it's been very, very expensive, very hard to deploy, very costly to deploy. So one of the things we set out to develop was to make this commercially available off the shelf at both a price that's accessible and using technologies that are very robust, so you don't have to be a PhD to be able to take this out and use it and get some reasonable imagery out of the system. So this is a good example of side-by-side comparison of the same target. So with a typical side scan, you see this image of a tow rope. This is a rope that was lost on the seabed. And we tend to find a lot of the images you'll see here are just junk. We find a lot of garbage on the seabed. If you're in any coastal community, they've been dumping garbage for probably hundreds of years. So you tend to find a lot of weird and wonderful little things on the seabed that make good resolution targets. So at a typical side scan at a 5-meter range, you get a great image of that tow rope. That beam width spreads with range. So at about 100-meter range, that's what that tow rope looks like. Using synthetic aperture sonar, as we're moving away from the vehicle or away from the platform, we're increasing the length of that aperture and maintaining that constant resolution. So whether you're at 5 meters or at 100 meters, the tow rope looks exactly the same. So this is some data collected, actually not too far from here, using possibly one of your boats. This was some data we collected on a towed system. So when we talk about synthetic aperture and using software to do it, this is actually data from our acoustic arrays. So this is the raw data. This is what it looks like if you just use that 1-meter array without any SAS beamforming. This is the kind of image you get. So this is what we would call real aperture using that 1 meter. Now we take exactly the same acoustic data and we run it through our SAS beamformer, and that's the data that we get out of the system. So as we're using all of these pings, so if you can imagine the vehicle's moving along like this, for one reason or another, most of the images you'll see are port side. There's no particular reason other than sometimes we image nice things on the port side. So the vehicle's moving on from the top or from the bottom to the top here, imaging out to the port side. So we're taking all of these pings and we're adding them up and we're compensating for the motion and we're building that synthetic aperture, and that's giving us this kind of image. And this is really important for if you're looking for targets on the seabed, or if you're doing any mapping, you're looking for anything that you might have lost on the seabed. Talk about little targets here, like is that a rock or is that a mine or is that the barrel that I dropped off the back of my boat? Well, when you start looking at the SAS data, you can very clearly see. The other benefit of adding up all those pings, and you'll see this when we get into the bathymetry, is we're drastically increasing the signal to noise of the images. So here we're very close to the nadir. which means we're close to the side lobes of the sonar. So there's very little acoustic returns there. So on a single ping, you're not really seeing much data compared to what you're seeing in the long range. When we add up all those pings in the synthetic aperture, we can actually start to see, oh, there's actually targets here, and there's some stuff that's interesting. Now, we still do get some shaded area here, and that's as a result of the platform was crabbing, and we're actually kind of doing some side slip as we're moving along, so that's why that dark area actually moves at an angle relative to the image. So you'll see a few more images like this, just comparisons side by side of the side scan images against the SAS image. And it's also important to note, and we'll talk a little bit about the beam forming process that we go through. All the images you'll see are formed in real time. So we're collecting this data, all these pings are coming in real time, we're feeding them into the beamformer in real time, and we're getting this image out. So you collect the data, and about 10 seconds, 15 seconds later, you get those images, and it's just continuously churning through the data as it's being collected. These are some targets that we use in a lot of our presentations because they're very interesting and they're very close to us in Canada. These are volos that were actually dumped in Halifax Harbour in Bedford Basin in Nova Scotia, east coast of Canada. There's 24 of these on the seabed. The history, they were damaged when they were coming over in transit from Europe. It was 1967 at that time. If they had landed with them, they would have had to pay duty on them and then not been able to sell them because they were damaged. So instead, they called up the Halifax Harbour Authority, said, do you mind if we shove these off the boat? They said yes, because it was 1967. They took the engines out, they took the wheels off, they drained all the fluids, and they literally shoved them off the back of the boat. So there's a line of these on the harbour. The Canadian Navy uses them as resolution targets because they know they're there, they've been there for a long time, they have lots of unique features. So this is what our Canadian Navy, and we're a little bit further behind in the American Navy, this is what we were using for mine hunting traditionally. And this is exactly the same targets at the same range using the synthetic aperture sonar. So this is a traditional side scan system. So you can start to see the benefits of that resolution. You can see the doors are open. You can see the roofs have collapsed. You can see they've removed the engines. But more interestingly, when we start looking at the interferometry, so the way we do our interferometry, we generate an image from the upper, there's two rows of elements in our arrays, as you'll see. We generate an image from the upper array, we generate an image from the lower array, and we cross-correlate those together to get all the phase differences. And then we run through a phase unwrapping scheme, and then we end up with the bathymetry that you'll see here. So interestingly, when you start looking at the bathy as well as the backscatter, you can actually see, so the roof is collapsed here, we can see the interior of the vehicle and the exterior at the same depth. So it's actually sunken down into the seabed. We can actually pick out the frame here, so we can tell here it looks like the roof might be intact, but there it's very clearly collapsed. And of course, we can see the doors as well on those targets. So what does this mean in terms of seabed mapping? Well, SAS gives you a drastically higher ACR, or area coverage rate, compared to traditional technologies, on the order of 10 times. And not only for mine hunting applications and target localizing search and salvage operations, but for bathymetry. So this is real bathy we collected in Halifax Harbour and another part of the harbour. So we've done a comparison just to illustrate what the area coverage would be from the SAS system compared to a multi-beam. Now we've scaled the multi-beam to show a 5 centimeter resolution. So how close to the seabed do you need to be to get a 5 centimeter by 5 centimeter resolution versus we're getting the same bathy resolution out of the SAS at a 250 meter swath. So not all applications require that kind of resolution, but if you need it, it's certainly available. And you can start to pick out, it's a little downsampled on the projector here, but you can start to see some of the anchor scour because there's a lot of boats anchored in that area on a regular basis. So what does the data look like? This is actually data collected in Narragansett Bay down in Rhode Island. So we ran the vehicle up and down this channel and collected all this bathymetry. We see some objects here, and this is interesting. One rare example where we're seeing objects in the bathy that we didn't necessarily pick up in the backscatter because the reflectivity or the returns from those objects isn't that high, but the bathymetric difference is fairly significant. So you don't necessarily, you can see some of them, some of the small dark blotches there. So this is a lobster pot. We have lots of images of lobster pots because there's a lot of them around, especially old abandoned ones that have been there for a long time. So at a 77, 76 meter range, you can see very clearly the shape of the lobster pot. That blurring that you see in the shadow region there, that's because there's no acoustic data in the shadow region. So we do, in our processing, we do a nearest neighbor approximation, and we actually generate, for every bathy pixel, we generate an uncertainty value as well. So in the shadow regions, because depending on the software you're using to visualize it, some software packages don't want to have nothing there. They want all pixels to be populated. So we put those pixels in with an approximation, and then we drive the uncertainty up artificially high so that you can easily filter them out when you're doing your post-processing or your charting. So when we're talking about resolution of bathymetry, just to give you an idea of how does SAS compare to some traditional technologies, these are the Volvos that you saw at a 6 by 6 centimeter resolution. So we're doing 6 by 6 centimeters in post-processing. We'll do 25 by 25 centimeters in real time on board the system. If you're running a typical multi-beam, you might be looking at a 50 by 50 centimeter resolution. You can start to see, well, the objects, there's something there, possibly man-made. When you start to look at an interferometric bathy system, a meter by a meter, now it's very hard to tell. Is that geology? Is it an object on the seabed? Is there anything there at all? So just to show you, using one of our products as an example, this is our INSAS, our miniature interferometric SAS system. It's a modular system, so it comes in a 60 centimeter or 120 centimeter length array. It's actually, the 120 centimeter is 2 blocks, 2 receiver arrays, so we can add or subtract as many blocks as we need. The interferometry comes from the 2 rows of planar elements in the array there. So we depress the array at about a 10-degree depression angle, and then we're running both of those at 337 kilohertz. And just to show you kind of what the area coverage is there. So we're doing the interferometry between those 2 rows of elements. So on this system, it's a fairly small interferometric baseline, meaning the vertical separation between those arrays. So one of the reasons, and I'll talk a little bit more about it later, but one of the reasons we have a longer array is we need to get that ping-to-ping overlap. To be able to get that overlap, you can't move faster than, basically you can't move more than half the length of the array between each ping. So that means if you want to go faster, you either need a longer array or you need to ping more quickly to make sure you're getting that overlap. So that's why we have the 60 centimeter, the 120, and we also have a 180 centimeter array. What does that mean in practical numbers? Well, operating at the same speed for a 60 centimeter array, you can do a range of about 120 meters. If you double the length of the array at the same speed, you can double the range because you're halving your ping rate. You're pinging twice as slowly. Or you can use the same array, run twice as fast, and obtain the same range. So that's where the trade-off comes from with SAS. That's also one of the reasons why there's a very strict stability requirement in SAS that we'll talk about as well. So there's a lot of different considerations when deploying interferometric SAS systems. Traditionally, it's very computationally intensive. People have racks and racks of computers to do the beamforming. It's a big data product. We're talking hundreds of gigabytes an hour. Our raw data rate is about 25 megabytes per second. The data recovery on unmanned platforms, untethered platforms, creates a bottleneck. Okay, you run out and you collect 2 terabytes of data. How do you get that back? How do you copy that data? How do you store it remotely? And visualization and post-mission analysis can be a challenge as well, because with any kind of large, high-resolution product, you've got millions of data points that you want to show all at once. How do you visualize that in your traditional post-mission analysis packages or your hydrographic charting packages? So this is what the traditional kind of SAS workflow, and we use an AUV as an example because most SAS systems tend to be deployed on AUVs. So the vehicle goes out, it runs, it collects data at 25 megabytes per second. Data recovery, even using a gigabit Ethernet connector, takes about 100 megabytes per second, so 4 times the rate. Then doing the data processing, the beamforming, even running 4 times real time, still takes a significant amount of time after you've recovered the data. Then we go through a georeferencing, data cleaning, environmental corrections, sound velocity corrections, tidal corrections, and ultimately then we do the mosaicing and the digital terrain modeling. So if you're running a vehicle for time T, say it's 20 hours, you have to spend 5 hours just recovering data, just downloading all that information, another 5 hours doing your beamforming and your data production. So you're spending up to 15 hours after the vehicle's recovered before you can even get an image out of it. So these are all issues that we wanted to address with a few different technologies. I won't go through the detail of it here, but I think the presentation will be distributed after the talk, so you can certainly, if you have any questions about how our processing workflow works, you can feel free to ask. Just to illustrate, though, one of the goals we had set out initially was to be able to do all of our beamforming in real time. We want to beamform as quickly as you're recovering the data, and actually faster than real time. So actual numbers, we've got a standard desktop machine using a GPU. We do all of our beamforming in CUDA. We use NVIDIA GPUs. So doing a matched filter, the motion compensation, and the image formation for 40 seconds worth of data, it takes about 8 seconds on standard desktop machine. On the embedded real-time processor that you'll see in the presentation here, you can see we're just 30 milliseconds shy of that. So we're still processing significantly faster than real time, even in the embedded onboard solution. So this is the real-time processor. It's about that big, 22 centimeters by 14 centimeters. It weighs about 3 or 4 pounds. The other technology we introduced was a removable data storage module called the data pod, which is basically a 4 terabyte NAS with a wet mateable connector on it. So when the vehicle comes back to the surface, you don't have to download data, you just pull that out, you can plug in a fresh one, send the vehicle back out on its way. We also partnered with Keras in the development of their Keras onboard software, because we're doing all the beamforming, we're doing all the image formation, and then we generate all these tiles that need to be stitched together, mosaicked, and we need to apply all those environmental corrections to them. So using a version of their HIPS software called Keras Onboard, it's basically a headless version of HIPS. It takes all of our tiles in, it stitches them together, it does the mosaicing, and it generates the digital train model to the point where when you get the vehicle back, there is no post-mission analysis to do. You have a fully formed data product ready to go. So with all these tools packaged together, you're running your vehicle, you're running all the beamforming on board the vehicle. It's doing all the georeferencing on board the vehicle. With the SoundView software, it's running all the data cleaning, environmental corrections, because we're programming it with the sound velocity profile and we're programming it with the tide tables, and it's generating the mosaic and the digital train model in real time. So when the vehicle comes back up, it's all there ready to go. Now, there may still be some tuning required. There's navigation drift issues that are faced. You may have the wrong sound velocity profile or need to change that. All that can be redone and the workflow can be repeated, but you don't have to do all the data recovery and you don't have to do all the beamforming again. So some sample bathymetry is relatively benign bathymetry. It was a somewhat flat bottom. This is actually data from the Baltic Sea. So we were towing the system at about 6 knots. Average depth of 50 meters. The towfish is about 13 meters off the seabed, and we get a swath width of 20 times the altitude. So we're doing 10 times on either side. So we're doing 130 meters on each side of the platform. So we went through and processed this data just to verify that the vertical uncertainty we were getting was as good as we thought it was. So this graph just shows you a slice of the uncertainty across that swath. Like any interferometric system, uncertainty increases with range. That's just a byproduct of the process. But even at the maximum range, well, maximum extends a bit further than there, but even at 100-meter range, you can see we're still well under a 10-centimeter vertical uncertainty 2 sigma, so at 95% confidence interval. So pairing this with a suitable INS and a calibrated depth sensor, and of course some tidal information, you can be well within IHO special order requirements for bathymetric mapping. So there are some limitations with SAS. So the speed limit is something that I was talking about a little bit before. The system can't move faster than half the array length between each ping. How does this translate into real numbers? Well, as we take a typical SAS system like our 120, we're increasing the speed, so from 3 knots up to 8 knots. What you can see here is the maximum PRI, which is the pulse repetition interval, is actually decreasing. So you have to ping faster and faster. The faster the vehicle goes, the faster you need to ping with a fixed array length. However, the interesting property is that because you're going faster and it's an inverse linear relationship, even though you might say you go twice as fast, you have your range, your area coverage rate actually ends up being relatively constant. There's some changes there because the gap size changes with altitude and other things. But so a INSAS 120, for example, does about 2.6 kilometers squared per hour of area coverage with a gap filler. Without a gap filler, and we define without a gap filler as actually doing overlap, about 40% overlap to fill the nadir gap, you're still getting around 1.8 square kilometers per hour. So the interesting part is that the area coverage rate is actually defined by the length of the array and not really the speed of the platform. People ask us a lot, well, can I go faster and get more area? Well, it doesn't really make that much of a difference. So you really want to go at the optimal speed for your platform in terms of the drag and the power efficiency, or on your boat, it might be the optimal speed for your stability. So you don't want the boat moving around too much. So this is just those numbers plotted out on a chart. As you can see, the different altitudes we have here. So there's a geometric limitation as well of that 10 times altitude limit. So that's based on the beam width of the sonar. So if you try and go, if you're at a 10-meter altitude, your maximum range is about 100 meters. You can set the ping rate to try and get out to 200-meter range, but then you start to get into the side lobe, the vertical side lobe of the array. So the signal to noise just falls off pretty dramatically at that point. So what you see is that all these numbers eventually max out the ACR, and this is actually based on our INSAS 180, which is on the Katfish system that I'll show you. They all top out at just under 4 square kilometers per hour, and that's driven by the array length. That's the constant value that you're seeing there. So how do you fill the gap? Well, there's lots of different solutions. People use multi-beams, people use forward lookers, people use other solutions to fill the nadir gap below the side-looking system. All of our numbers, we really petition for people to do a certain amount of overlap, 30 to 40% overlap with the gap filler, and I'll show you why in a second here. If you can fill the gap, you get about a 40% increase in your area coverage rate. But the problem that you have when you're trying to fill a gap, if you're say doing mine hunting, you're probably filling it with a forward-looking sonar, or if you're doing bathymetric hydrographic work, you're filling it with a multi-beam. So using a multi-beam as an example, and we just took 2 standard multi-beams, so a Norbit and an R2 Sonic 2022. When we're talking about resolution, okay, at low altitudes, yes, you can get the multi-beam resolution at close to the resolution of the SAS, which in bathymetry is about 25 centimeters, so that's why you see that constant line there. But as soon as you start increasing your altitude, you get drastically lower resolution. So yes, you can fill the gap with a multi-beam, but then you have a kind of swath in the middle of your data set that is at a different resolution, which, depending on the reason that you're doing the survey, may be a problem for you. There is something that we're working on, and we'll touch on just a little bit here. We're developing a way to actually use the SAS as the gap filler. So one of the reasons that we have this relatively large nadir gap there is both our receivers and our transmitters have a very tight vertical beam width. So we're actually not transmitting any data down into the nadir. Now, if you've ever used a typical bathy swath system like an EdgeTech 6205 or 4200, they will give you full nadir coverage, and what they're doing is they're actually pushing energy into the nadir, and they're using the side lobes of the array to do that. Well, with the SAS, it's a little more challenging because we have to do that synthetic aperture. So you can do that up to a certain point, but basically once you get right below the platform, the problem you face is you can't tell whether the ping's coming from the left side or the right side, so you end up with a little bit of a singularity there. But it's still something that we're working on, and that's one of our engineering challenges at the moment. So we can get into some of the results, the actual application of this stuff. So operating our real-time SAS on a Minas 600, this is owned by the DSTO, which is the Defense Science and Technology Organization in Australia. A lot of what we do is in very shallow water, and which is most of the mine hunting work that happens. But it also creates an extremely challenging acoustic environment. You have a lot of multipath, you have a lot of motion in the boat, and you end up with lots of stuff on the seabed that you need to avoid. So we did a trial, we did 2 trials actually, one in Sydney Harbour in Australia, and the other one in Jervis Bay, which is about 3 hours south of Sydney. So 2 very different locales and different environments, but at roughly the same altitude. So between 5 and 10 meters depth. We ran the vehicle at a 5-meter altitude. We figured we would get a 100-meter swath, so 50 meters per side, 10 times the altitude. And they laid out a bunch of targets for us to look for. So here you can see the vehicle is actually, so there's the nadir gap. The vehicle has run out here, turned around, come back. So this data set is just from the return leg. So we have the nadir gap. This was from a dual frequency system. So we have a short range, high frequency there, and then a long range, low frequency. And what's really interesting, okay, here we can see the pier. This is one of the Navy bases, Creswell, I think. But more interestingly, we see this big black area here. So what's happening here is the sonar, so the vehicle, as I say, is driving along here. It's imaging up on the port side, imaging up actually into the shoreline. So that big black area that we're seeing is air, essentially. There's nothing, we've actually run right into the shore. And when we talk about multipath and very shallow water, this is one of the extremely challenging areas to operate in. Because if you wanted to take a multi-beam on a boat and survey this area, well, you're not going to run right up to the shoreline there. You would have to use an airborne LiDAR system or some other kind of system to collect that data. Whereas, and with a traditional side-looking swath bathymetry system with a single ping, the multipath dominates the signal so much that you just wouldn't get anything of any value in that area. But with the SAS, because we're adding together all of these pings, the multipath is incoherent noise, so we're actually filtering out a lot of that noise. You still do see a slightly lower signal to noise in these areas, but you can image right up into the shoreline, and you're getting viable both imagery and bathymetry. Now, we have a nice square box there, so you can see we didn't really generate bathy on the shore. We just artificially filled that in to make a nice square box. So out here, it's about 10 meters depth. Up here, it's just over 5 meters. So the vehicle is just below the water, and it's imaging right into the shoreline. So this is the data further south. This is in Jervis Bay. So we ran the vehicle up and down here, running the real-time SAS system. So this is running on board the vehicle. It's doing all the georeferencing. It's doing all the mosaicing. So at the time, we were just using Google Earth as a visualization tool. So the vehicle came to the surface. We had a whole bunch of geotiffs and KMLs. We dumped them off, and this is the data that we got out of it. There's one small artifact there. The X doesn't mean anything. It's just a Google Earth issue. But we're running about the 5-meter contour is probably about here. The 10-meter contour is here. The 5-meter contour is there, and we were oversampling on either side a fair amount. And there's some of the bathymetry from the area. So again, we just took one leg out. One of the problems with AUV data is drift, navigation drift. So when you start combining multiple legs together, then you start seeing these offsets that are accumulating. So you can take those out by post-processing with a USBL system or by trying to kind of massage the data a little bit. But when we're just looking at visualization, we just take one leg at a time. So in context there, they put out, even though they weren't overly concerned with the bathymetry at the time, they were more concerned with these targets that they put out there. So they put out 8 targets. We located 8 targets. And when we talk about area coverage rate, so it was a 0.5 square kilometer area. Duration took us about 30 minutes to do the mission. So we achieved our 1 square kilometer per hour area coverage rate that we were expecting. And there's the vehicle fully loaded with the sonar on there. So what about towfish? And that's one of the areas when we start getting into high speed, well, an AUV can only go 3 or 4 knots. If you want it to go much faster than that, you're going to have to waste a huge amount of battery power for not a lot of benefit. Surface-mounted systems have other problems with them. Towfish, you can, with an actively controlled towfish system that we're going to be talking about, why use an active system? Well, you can get a much better image quality because you can fly very close to the seabed. You can do single pass classification, meaning you don't have to go over the area multiple times. You can get all the information you need in one pass. faster tow speeds is one of the biggest benefits of going with a tow body. So you can drastically increase your ACR. We put a much longer array on the system. We can run at 8 or 10 knots. You can cover a lot of area in a very short period of time. And one of the important reasons, if anybody's ever operated a towed sonar, one of the important reasons to be active is bottom following and bottom avoidance. Anyone who's towed anything has probably driven it into the seabed at least once. SAS is, even though we consider it to be low cost, it's still an expensive item. It's not something you want to drag along the bottom. So having some intelligence, and our background in our previous company where we spun out of, we were actually building AUVs. So a lot of our experience is in obstacle avoidance, autonomous navigation, and fault responses. So I talked about SAS stability requirements. These numbers you see here have been very well vetted. We've put our sonar onto a whole variety of different platforms that haven't been tuned well, that aren't hydrodynamic. We've slung it on the bottom of systems. We've even towed it from a rope just hanging below a speedboat. So we've gotten some very, very good data and some very bad data, and somewhere in between been able to validate very precisely these numbers. So we know without even integrating onto a platform, if you have a tow body or an AUV or even a surface vessel, if it can meet these numbers, you will get good SAS data out of it. The reason that we need that stability is for that ping-to-ping overlap. That's the critical thing all the time. So both you have to have the ping rate and the speed set correctly, but if the platform's pitching too much or it's rolling too much and you're outside of the beam width, if you're not insonifying the same area again and again, then the motion compensation will break down and you won't have a synthetic aperture anymore. You'll just have the real aperture sonar. The advantage is if it's a particularly bad day, if the stability is bad for whatever reason, it does just degrade into a side scan. So the worst case scenario, you end up with side scan data. So why towed systems? We had a lot of people wanting to bolt this sonar onto, like they would with a multi-beam, a pole mount or a bow mount system. This very clearly demonstrates, and this is real data from one of our sea trials, the difference between what the boat is doing and what the towfish is doing. And this was on a very flat day. So the boat, we're seeing a pretty steady pitch oscillation there, which is you will see on any surface vessel of 4 to 6 degrees. Whereas the tow body, and this is without the control system active, just towing the vehicle behind the sonar or behind the boat, you can see you still see some of the same oscillations, but the amplitude is significantly lower. So the tow body is significantly decoupled from surface motions, meaning you can run in higher sea states, you can run in different environments. The quality of the data is directly affected by the stability of the sonar, even with a pole-mounted system. The tow body can achieve the optimal geometry, meaning it can get close to the seabed. So if you're on a hull-mounted system on a 200-meter water depth, that means you're 200 meters away from the bottom and your resolution is going to suffer. Whereas with a towfish, you can get it right down to the seabed and get the optimal data. So we build an active, the Katfish is the Kraken active towfish. We build an active system. Why active and why not passive? Well, this is the output from a passive towfish. A passive fish, just a dumb tow body, can't compensate for the motion or the disturbances. So if you shake that cable, you have to wait for those oscillations to naturally damp out. And this is the kind of result that you get out of that system. So the pitch roll yaw rates grossly exceed SAS thresholds. Generally, in a sea state 3, generally we say you're only getting SAS stability. You'll be able to get it sometimes, but only about 67% of the time. And it'd be a hard thing if you said to your customer or your surveyor or your research organization, I'm going to go collect data and I'm going to throw 40% of it away. So we wanted to drive that number up. So why active? Well, it significantly improves the pitch roll and yaw rates on the system, as well as having the bottom avoidance capabilities and all those other wonderful things, to the point where we end up being about 95% of the time you're within the threshold, the stability threshold of SAS. There's always something that happens that will exceed the ability of the vehicle to compensate, such as in turns, for example. So you do have large spikes in a turn, or if you hit a particularly large wave. But with an active system, it can recover very, very quickly from that. So the tow rope data I showed before actually came from our towed system. So that's the kind of data, and this was at about an 80-meter range. We tend to show a lot of zoomed in targets because Otherwise, you just see a little thing on a very big area coverage, and it doesn't look very interesting. So georeferencing is a big challenge with any towed system. Okay, when you have a pole mount system on a surface vessel, you have an INS, you have a GPS, you have maybe RTK, maybe you're aiding it with a base station, something like that. When you have a towed system underwater, even though you know that it can't be more than the length of the tow cable away from you, the position is still somewhat unknown. So we tackle that in the same way we tackle it with an AUV, in that we have a GPS on the surface vessel with an INS on the surface vessel, so we're compensating for the motion of the surface vessel. We have a USBL system on the top side, and we're fusing that USBL position fix with both the cable length that we know, and there's an INS on board the actual vehicle itself. Plus, all that motion compensation we're doing in the SAS, that ping-to-ping correlation that we're getting out of it, we call that's a correlation velocity, or a correlation velocity log, CVL. So we're taking all those velocities coming out of the system, we're feeding that directly back into the INS. And I won't get into the details, but for a lot of reasons, that correlation velocity is much, much more accurate than a typical DVL or other velocity measurement. To the point where with our standard kind of low end positioning system, we're doing about a 4.5 meter horizontal accuracy at the maximum range, meaning so when you have 1,000 meters of cable out and 220 meters away from the fish, which is the maximum range of the sonar, you would know where that target is within about 4.5 meters. When we move up to the advanced solution, which is going to like a fiber optic gyro-based system, that comes down to less than a meter of accuracy. So this is the Kraken towed system, our active towfish. You can see it there during sea trials. That was actually a few weeks ago in Newfoundland. So this uses our INSAS 180, which is a 180 centimeter array. The reason we go to that very long array is because we're towing it very fast. So we want to go very fast and get a long range. So we use a longer array. That'll do a swath width, and it depends on water temperature and bottom type a little bit, but that'll do a swath width of about 480 meters, 240 meters per side. We have an operating depth of 200 meters. That's really rated based on the cable. So we deliver it with 1,000 meters of cable, meaning at 8 knots with a 5-to-1 layback, you can tow it at about 200 meter depth. All the components, the SAS, all the pressure vessels, everything are rated for much deeper than that, but we limit it on the cable scope. So the whole system, the whole concept is built for a ship of opportunity, and that's why we have all that positioning system infrastructure built into the whole fish. So you don't have to take it out on a boat that you have set up and calibrated with your moment arms on your INS and all of these things. You can just drop this on the back of any boat that you happen to have available. It has the GPS, USBL, INS, everything ready to go. You do a patch test the same way you do any other patch test, and then the system is fully calibrated. So there's the system. This is a particularly good day. Right now there's a lot of ice in the water in Newfoundland, so I was very happy to see that it's sunny here. So this is the tow body. It's actively controlled on the tail fins there. So those 4 actuators actually move to control the fish. There's the There's the USBL there on the top side, and then it's a hairy fairing on the cable to reduce the drag of the cable, and a fixed depressor wing, and then the INSAS 180 is actually mounted on the side of it there. So to show you some more of the data examples, we weren't using the Katfish in the Arctic. We were using an AUV-based system because we were operating under the ice. You can't tow something under the ice. So this is the bathymetry. So when you're running the real-time system, it's doing all the beam forming. When you're running the Keras SoundView software with that, the vehicle comes back to the surface, and this is what you get. This is the bathy that comes out of it. It's all stitched together. You can see there's a few artifacts there on the edges that need to be filtered out. But what you're seeing here is iceberg scour, which we saw a lot of that up there. And then eventually, I don't know if you're familiar with it or not, but the reason we were in the Arctic, we were looking for the Franklin shipwrecks. We found one of them. 2 years later, they found the other one. But it was a fascinating search effort, because if you look at the hydrographic charts, in that area, there's one narrow strip of soundings in the middle of Victoria Strait. That's the only soundings that exist. Everything else is just white. So every boat that ever runs through there goes on that same route, because that's the only one that's ever been surveyed. So when we said we wanted to go out and search for this vessel, we were searching in literally uncharted waters that had never been mapped before. So an AUV was an ideal tool for that, because one, there's no people on board, there's no risk. Two, the AUV is very agile and it can avoid the bottom and things like that. But it was really interesting to look at the data because we're looking at data that no one had ever seen before. And you see some of this iceberg scour is 5 meters, 6 meters deep, meaning that there was, and then 50 meters of water, meaning there was a massive iceberg moving through that. We do a lot of, on the commercial side, do a lot of pipeline surveys. So this is actually in the Baltic Sea. This is I think this is the Nord Stream pipeline. Some sections are buried, some sections are on the seabed, and then they just do some dumping there to try and keep it from moving around. So there's obviously some sand waves there. You can see every 11 meters, I believe, there's actually a joint band there, and that's one of the reasons they're doing that survey is they're checking to see has that band failed. Do they need to go down and service that? This is from Florida, actually, this data near Riviera Beach. So complex seabed types, the system, a SAS, our SAS, but lots of SAS systems will have a very high dynamic range, meaning that you can image both very soft targets, soft sediment, mixed with much harder targets at the same time, and you're not going to saturate and then have to go back and retune your gains to run over the area. It can collect it all at the same time. So we've capped the just for visualization, we limit it to 30 dB, but it runs all the way up to 65 dB. So you can see if you did start to drive it up, you'd see some of these highlights change a little bit, and you start to pick up some of the features of what's on the seabed. We do a lot of resolution tests. So we throw something that we've built or our customer has built into the water and then do a survey in the area. This is a resolution target, so at about a 70-meter range. These are 5 centimeter, America, we're 2-inch spheres separated 2 inches apart. We're metric in Canada. So. So there's 4 of these on each arm and then 1 in the center, and you can see there, you can actually count the arms or the spheres. This is just a crude illustration of what that target looks like. You can tell Jeff prepared these slides because he's got the inches in there. There's some what we call MLOs, mind-like objects, out there doing that work as well. So a lot of what we do, although mine hunting is definitely a big thing, a lot of what we do is just looking for stuff, things that fall out of the sky, things that are, whether it's shipwrecks, whether it's faults in pipelines, whether it's something on the seabed. Finding something that's relatively small in an area where you have a lot of targets is a huge challenge. So this is where when we talk about, well, do you really need 3 centimeter resolution over such a large area? If you're looking for something like this, definitely, to be able to differentiate it between all these other targets. And this is the bathymetry from that area as well. So that's the actual mine there, and then that's the shadow region that you're seeing. So that's artificial data there. So the vehicle was running, again, the vehicle's over here. This is a single side and this is actually a single tile. So the SAS data comes out in these tiles of data that then get georeferenced and stitched together. So this is port side again. So the vehicle is running here. The nadir starts at about 20 meters up to about 100 meters. So we're at a 10-meter altitude, meaning our max range is about 100 meters. And there's a slope in this area as well. So this is some of the kind of more esoteric work that we're doing. We call it circular CSAS, circular SAS. It's not really circular. We just do multi-aspects in straight lines and then combine them together. The interesting thing is, so you take SAS, you have very high signal to noise in SAS because you're adding up all these pings. Well, you can do the same thing if you take multiple SAS images of an object from different or different angles. So you'll notice these are a bunch of different, I think we took a dozen of these images to get the one on the right. So you'll notice the object there, which is a small truncated cone. There's a rock nearby, and you'll notice that even though the shadow moves, the rock doesn't, because the rock is stationary. So we're coming at it from multiple angles, and then we recombine all of those images together to give you one target that doesn't have any shadow. So this particular target actually has 4 lifting hooks on it. So there's 1, 2, 3, and then that 4th one, I think we undersampled that. But combining that, so previously you saw the shadow region, the problem with the blurring in the shadow region. Well, as soon as you eliminate the shadow, you get a much better bathymetric result as well. And then we can overlay the backscatter on top of the bathymetry, and you can actually start to see some of where the highlights are located there. So in conclusion, there's a lot of information there, so I'm happy to take questions, but just to drive home the point that, interferometric SAS, previously thought to be something that was reserved for military applications or people with very deep pockets. It's commercial, off the shelf. Traditional challenges with SAS, there's a few technologies that we've developed to specifically try and address those, and of course we're continuing to innovate and continuing to try and make it easier to use and having less knobs to tweak and more automation in the system. Active tow bodies can be deployed from a vessel of opportunity, and we've done a number of examples of that. And most importantly, the imagery and the bathymetry far exceeds, I would say, the range and resolution of what you can get out of traditional sonar systems. And that's it. Happy to take any questions. Yep.
You talked about attitude kind of limitations. What about sound speed? One of the advantages of working low is you're out of that dynamic region, but if you're towing it or near the surface.
So the interesting part was, so if you go through a sound like a halocline or a thermocline, yes, you're relatively close to the bottom, especially in deeper water. You don't have that issue. It tends to be pretty homogeneous. Shallow water, we see a lot of sound speed variation. In 5 or 10 meters, you can go from 30 degrees to 15 degrees or lower. The interesting part of the SAS is, so you're transmitting a signal, you're receiving that signal back through basically the same sound profile, and because of the ping-to-ping correlation, so what will happen is you'll always end up with a well-focused image, because it will try and motion compensate for what it's seeing the return as. But what will happen is the actual slant range may change, so you'll get ray bending effects essentially. So things will move, but the target itself, the whole tile, will still look well-focused. So the output, if you do have multiple sound profiles across that whole range, you can reproject the actual bathymetry as well, just like you would do with a typical multi-beam system. Yep.
So your Sydney Harbor example, you kind of flew by, quickly mentioned high frequency and low frequency.
So we have.
What is that? And is it standard? And
I didn't want to go through our whole product portfolio. We focused on the INSAS here because it is smaller and it's more common for us. We have more of those systems out there. This is actually what we call an INSAS. It was our first product, just Interferometric SAS. It uses 2 separate arrays, so the vertical baseline is between those 2 arrays, but each array has 2 rows of elements, and I figured I'd need a whiteboard. Yeah, possibly not right. So we can probably illustrate this without the whiteboard. So there's a long-range low-frequency element, and then angled at 17 degrees, there's a short-range high-frequency element. So we actually split the coverage into 2 distinct swaths. So it's almost like we're running 2 sonars at the same time. And when I say low frequency, it's running 240 kilohertz, and the high frequency is running 337. So the advantage of that, especially in very shallow water, is that it drastically reduces the multipath. So we've got 2 very narrow vertical beam widths covering that area. So the INSAS is a smaller system, but it just uses 2 planar elements instead of 2 arrays with offset elements. So the shallow water performance is affected a little bit. It's a little bit better in the INSAS than the INSAS system, but it is a standard product for us. So this was our first product in that system. I hope that makes sense.
It does, yeah. Okay. I was going to ask you how you make those images without multipath.
There is multipath. We just
avoid
it. Okay. Any other questions? Nope.
All right. Well, thank you for coming, and thanks for everyone for a great seminar.